Hello and welcome back to chemistry. So we're talking about right now are acids, and specifically the different classes or categories or types of acids. We're going to talk about three classes of acids today. We'll talk about binary acids, we'll talk about oxyacids, and we'll talk about organic acids. Now, the first class that we're going to talk about, binary acids, are one that should be reasonably familiar to you from your previous chemistry class. Binary acids are basically binary substances that are also Arrhenius acids. Now, remember, a binary substance is what a substance composed of only two elements. And a binary acid is therefore, well, one of them is going to be hydrogen and the other one is going to be a different element. Now, you already saw the binary acids made from halogens. Hydrofluoric, hydrochloric, hydrobromic, and hydroiodic acid. And back then, you may have been curious as to why these acids have the word hydro in their name. You know, when we're talking about an acid, why are we using the Latin word for water in describing it? Some of you might have thought maybe it's because it's short for hydrogen. It's not. It literally means water. A unique property of these binary acids is the acidic properties that we associate with them only become prominent when these materials are dissolved in water. This is one of the things that confused Arrhenius a great deal. For example, when he took hydrogen chloride and he bubbled it through, say, aniline as a solvent, which is neither protic and it's not water. He saw none of the classic properties of acids. Didn't turn litmus red. If you taste it, and I do not recommend doing so, it did not taste sour, and so forth. The various properties that we associated with acids for these materials, they only take place when you form a mixture of these materials with water. So it might be reasonable to say that that these substances themselves are not so much acids as as materials that become acidic solutions. So, for example, if we name these things, if somebody talks to you about HCl, well, technically they're talking about hydrogen chloride. HCl means hydrogen chloride. HBr means hydrogen bromide, a binary compound that has no acidic properties. It only forms an acidic solution when you mix it with water, and that's why the formula for hydrochloric acid or hydrobromic acid is actually, the formula for this is actually HCl parentheses AQ, indicating that it is only hydrochloric acid when it is in the aqueous state. So if someone says hydrogen bromide, what's the formula? Just say HBr. If they ask for hydrobromic acid, then you say HBr aqueous. And there is a difference between these two materials. In fact, one of these is a material and the other is a mixture. Hydroiodic acid is HI aqueous. And HF, well, what's the name of HF? Again, hydrogen fluoride. And HCl aqueous is hydrochloric acid. That's an important distinction. All right, but you learned about the binary acids that were composed of halogens previously. We're going to add a few more to the list. If you form a binary compound with the chalcogens, the period right next to the halogens, well, these materials are also binary acids. For example, H2S is when dissolved in water is hydrosulfuric acid, hydroselenic acid, and hydrotelluric acid. And yeah, water, the one on top of the list, water is an acid also. Now, if we try to apply our previous criteria as to, when these things dissociate, which of these is a strong acid, a weak acid, and a negligible acid, well, the hydrochloric, hydrobromic, and hydroiodic acid dissociate completely. They are, in fact, strong acids. Hydrofluoric acid, as we've already mentioned, is a weak acid that only dissociates about 5%. Furthermore, the acids of the chalcogens, hydrosulfuric, hydroselenic, and hydrotelluric acid, are also weak acids. And water we're going to get into a little bit more as we go forward, but water is an acid, but it's a negligible acid. And that's a very important distinction. It can be pushed into acidic behavior, but when you put water, say in water, the dissociation of the water is very slight. We'll talk about water as a special case as we go forward. All right. So how do we explain these things based on atomic structure, molecular structure? How do we explain this difference that seems to indicate that something like, say, water is the least extreme one on that tile, and then we've got 3 red ones on that tile as well. There's a couple things that we can look at with regard to with regard to the acidity. Well, one of the things is delta En does make a bond a little bit weaker. So the greater the difference in electronegativity, that is going to affect the acidity. That's why, for example, the halogens are more acidic than the binary acids made from chalcogens. But a more significant issue is atomic radius. If you look at atomic radius, which increases as you go down, basically as you go down the periodic table, the bonds get longer. And you might wonder, well, what does the length of the bond have to do with acidity? There's a trick you can play with a friend. Ask that friend if they can break a pencil. Show them a pencil. They'll say, oh yeah, quite easily I can break that pencil. Then maybe make them a bet. Say, tell you what, buy me lunch. If you can't, if you can, I'll buy you lunch. When they agree to it, then go to the pencil sharpener and whittle it down to about that big. Hand it back to them. Say, okay, break the pencil. The thing I'm trying to illustrate here is longer bonds break more easily than shorter bonds. And this is a significant property with regard to acidity. And this is why, if you look as you go down that list, the acidity increases because the dissociation increases because it's easier to break a longer pencil than a shorter pencil. All right. So if somebody asks you, of these, which is the strongest acid of these binary acids? The answer is hydroiodic acid. That's the strongest of those acids. And if you ask which is the weakest of these acids, well, water is the weakest. But basically, as you go up the halogens from hydroiodic to hydrobromic to hydrochloric, it becomes a weaker acid, and the strength of the acid weakens. Those 3 are still strong acids. Hydrofluoric acid falls in the camp of a weak acid. All right. So this puts us in that larger grouping of all the acids that we were talking about. Again, 3 of these are in fact strong acids: hydrochloric, bromic, and hydroiodic, which add to hydrosulfuric, sulfuric acid, nitric acid, and chloric acid and perchloric acid make the 7 classic strong acids. Hydrofluoric acid and all of the acids of the chalcogens and acetic acid fall in that weak camp. And so far, the only negligible acid we're talking about is water. All right. Okay, now let's talk about oxyacids. So the next classification here are the oxyacids. Now, what are oxyacids? Oxyacids are acids made, they're pseudo-binary compounds that are made from hydrogen and an oxy ion. Remember, oxy-ions are what happens when oxygen basically dogpiles on a monatomic ion. If I have, for example, the phosphide ion, and I start dogpiling oxygen on top of it, then I can form a polyatomic ion that I can use in much the same way I can use a monatomic ion, including to make acids. So if I take the phosphide ion and I put 1 or 2 or 3 or 4 oxygens on it, if I've got like 4 oxygens on that, I can then use that plus H plus to make an acid. Remember, the way you name these oxy ions is based on the underlying element. If you have phosphorus in the underlying element, then you have either the phosphate or the phosphite ion. And nitrogen is the nitrate or the nitrite. The 8 is always the big one. Think Thanksgiving, right? I ate more in Thanksgiving. More oxygens is the 8. And the dividing line is usually between 2 and 3 oxygens. Phosphorus and sulfur are bigger atoms. They can hold more oxygens. Their dividing line is between 3 and 4 for the phosphate and the phosphite ion. The others, the dividing line is between 2 and 3 oxygens. That's true for carbon, nitrogen, bromine, iodide, and chlorine. However, you also have to remember the charge on these things. So it's not enough to know that the chlorate ion is 3 oxygens. You have to know the charge on it. Well, the good news is it's usually the underlying ide ion, just with neutral oxygens stacked on top of it to form a polyatomic ion. So, for example, if the ide ion, the chloride ion is -1, then the chlorite and the chlorate is also -1. That's same with the bromate, same with the iodate, chlorate, phosphate, nitrate, sulfate. Nitrate and carbonate, or nitrogen and carbon, are different. So although the sulfate ion is the same as the sulfide ion 2-, when you get to carbon, well, carbon's a more complicated story. You kind of knew that was going to happen. When you get to carbon, the charge on the carbonate and the carbonite is 2-, and nitrogen is kind of like carbon's little brother. He tags along, tries to do the same thing as carbon to a lesser extent. So nitrate and nitrite is 1-. It's not 3-, it's 1-. But using those rules, you can usually figure out the names of these materials. You can name the underlying oxy ion. As a heads up, you can stack more than the most. You can supersize it. We have the chlorate ion with 3 oxygens on it and a -1 charge. If you supersize it, you can put 1 more oxygen on it. That's 4. That's the perchlorate ion. And you can get under the least too. Just like a hypodermic needle can get under your skin. You can get under that smallest number of 2 with a hypochlorite ion that has only 1 oxygen. And technically you can do this on all of them, but the only place you'll see it is in the halogens. Okay, so these are the oxy ions. Once you take those oxy ions, the next step is to add hydrogen to them. The sulfate ion's got a 2- charge, so give it 2 H pluses. And now you have sulfuric acid. The nitrate ion has 3 oxygens and a -1. Give it 1 H plus, and now you have nitric acid. Going from the oxy ions to the acids is pretty simple. Just think 2's company, 3's a crowd. Whatever the underlying oxy ion is, the bigger one will be the ic acid, nitric acid, sulfuric acid, phosphoric acid. The bigger one will be ic. 3 becomes ic, and 2 becomes us. Just think 2's company, 3's a crowd. 2 is us, 3 is ic. And so the nitrite ion becomes the nitrous acid. And also be careful with phosphorus and sulfur. Their dividing line is 3 and 4. But again, the big one is ick and the small one is us. All right, that's how you name oxyacids. Now we should talk a little bit about the strength of oxyacids. All right, there's a couple things to consider here. When we were looking at binary acids, the first thing we looked at was, the bond length. And then we also looked at the electronegativity. Okay, so what makes this an acid? What is it more likely to be able to break, for it to break off? It is more likely to break off if we have the longer bond. But again, be careful here. The hydrogen isn't attaching to the nitrogen or the bromine or the chlorine, the things that differentiate these. It attaches to an oxygen in each case. So the bond length in oxyacids doesn't change. The other thing was electronegativity, and the electronegativity has more impact when we are talking about these acids. If you have analogous oxyacids, like the hypochlorite acid, hypobromite, and hydroiodite acid, you got to ask yourself, well, what does that difference do? Well, the more electronegative element will pull the electrons more off of that oxygen, and therefore it's going to have less strength to hold on to the H+. So the more electronegative element in an equivalent series, like hypobromite, hypochlorite, hypoiodite, the more electronegative element will make it more acidic and more likely for that hydrogen to break off. Now, another factor that doesn't exist in the binary acids is the number of oxygens. Remember, you could have, for example, with chlorine, you could have the 2 or 3, the chlorate ion or the chlorite ion, and therefore the chloric acid, 3 oxygens, or the chlorous acid, 2 oxygens. And you might ask yourself, well, more oxygens, does that make it more or less acidic? Makes it more acidic. More oxygens, more acidic. In fact, perchloric acid, 4 oxygens, is one of the strongest of the classic strong acids. Chlorous acid, chloric acid, which is 3 oxygens, is right on the borderline. It is right on the borderline between the strong and the weak acids. And then chlorous acid and hypochlorous acid, they become weak acids. So why is this? Why is it that the oxygens, less oxygens means it is less acidic? It's because once you pop off that hydrogen, you can now stabilize the negative charge with resonance structures. You can disperse that negative charge across more atoms, and therefore the oxygen, the ion can handle the loss of the H+ better. So more oxygens, more acidic. You do have to realize there are 2 different trends here: electronegativity and number of oxygens, and they can be in conflict. So you really can only tell the relative strength, off the cuff, if you are looking at an analogous series. All right, so if I gave you these, for example, HCl, HI, HBr, HF, and I asked you which is the stronger acid, could you tell me? What do you think? Which one of these is the strongest of the acids? I mean, chlorine's, fluorine is the most electronegative, right? Greatest difference in electronegativity should mean it's a weaker bond, easier to break, but it's also a smaller atom. And remember, the longer pencil is the easier one to break. So again, which one is the strongest acid? It's the hydroiodic acid. Hawaii rules, okay? How about these? If I gave you this series and I asked you, which one of these is the strongest acid? We're looking at, looks like hypobromic acid for the first one. We're looking at bromic acid for the second, bromous acid, or perbromic acid. Which one is the strongest of those acids in that series? It's going to be the perbromic, right? More oxygens. If they all have the same halogen, the same central atom, more oxygens stabilizes it more. There's more we could do here, but If you're looking at HF or HI, which one is the stronger of the two? Well, again, HI is a strong acid, HF is a weak acid. Perchloric or chlorus, again, chlorus acid is a weak acid. But chloric acid, perchloric acid, it's one of the strongest of the strong acids. Look at the blue ones, hydrochloric acid or hydrobromic acid. Which one? Well, for the binary acids, look at bond length, not electronegativity. Hydrochloric acid has a greater difference in electronegativity, but it's about bond length with binary acids. Hydrobromic acid is actually the stronger acid. A lot of people will get that one wrong on a standardized test. How about the red ones? Perbromic or bromic acid. Again, more oxygens. The perbromic is going to be the one. How about the blue one underneath that? Hypochloric or hypobromic acid. Be careful. This is exactly the opposite, the trend for the binary acids, where hydrobromic acid was stronger because of bond length. But here, the hydrogen is on the oxygen, same bond length. So now you look at the electronegativity. And hypochloric acid will pull the electrons off the oxygen more and therefore make it more easy. A hypochloric acid will be stronger, even though hydrochloric acid would not be as strong as hydrobromic acid. All right. You can and you should play with these a little bit more as you go through. The next thing we're going to talk about is in the structure of acids is organic acids. And we're not going to get very deep into this. It's just you should be aware you're going to see some organic acids and you should know where to put them into this puzzle. What is an organic acid? An organic acid is basically something that looks like carbonic acid, but has some kind of alkyl residue stuck onto it. Acetic acid, for example, with a methyl group here, and then carbon, carbonyl, hydrogen, and an oxygen. Anything with that functionality has acidic properties. It's basically a little catapult. What's happening here is that that carbon-oxygen double bond is like a pulley, and the electrons can go up and down on that. And it can therefore pull the electrons away from that other oxygen and then launch out the H plus for you. And whatever you put there, that's just a carbon with 3 hydrogens, a methyl group, but whatever you put there is how you can attach to these larger organic structures acidic properties. Citric acid, maleic acid, formic acid, these are all organic acids. And but they all have basically that same catapult thing. And so the thing is, as varied as organic acids are, and they can get extremely varied, and there's a lot more complexity too there. At the top level, at the highest level, basically just look at it as the same functionality, where I have HOCO and then something on the side. In this case, that's acetic acid. And all of these are going to have about the same acidity. They're all going to be weak acids. For the most part, there's probably an exception, but the ones that you're going to run into, treat them all as weak acids. Furthermore, they will all dissociate about the same as acetic acid, which you already know dissociates about 5%. So all organic acids, and you can recognize them as some organic and then carbon, double bond O, oxygen, hydrogen. All organic acids you'll throw in the camp of weak acids. All right, that's what we got for you now. Next up, we will get into Bronsted and Bronsted-Lowry acids, the best team that wasn't really a team. I'll see you next time. You have a great day.